Hey Ramblers! This video covers the second half of Chapter 2.1 in our textbook, and we're going to continue our discussion of instantaneous velocity, and we're going to begin to picture it on a Cartesian plane. So what does instantaneous velocity, or how does average velocity become instantaneous velocity when we look at it on a curve? You'll recall from the last video that average velocity was the change in position over a period of time. And then to get instantaneous velocity, that period of time, we took the limit as it went to 0, and we started calling it h. So instantaneous velocity became the velocity at one point, or two moments in time, literally right next to each other, as that difference between them was becoming 0. So we want to look at that graphically. And so I've set up 2 points on a graph that we'll be looking at later, and you're going to see how the secant line becomes the tangent line, how average velocity becomes instantaneous velocity. So we're going to associate a secant line, which you'll recall from geometry was a line that intersected a circle or a curve at 2 points, and how that becomes a tangent line, which, as you recall again, was a line that intersected a circle or a curve at just 1 point. So instantaneous velocity will be represented by the tangent line. Average velocity will be represented by the secant line. All right, Ramblers, again, this is a very, very central topic to this first semester and even really to the whole year or to the study of calculus. So pause often, take good notes, and really try to make sure you understand. And if you don't, try to figure out what questions you have so that you can get that cleared up. All right, pause often, take good notes, and thanks for watching. Okay, it's really important that we learn to apply the concept of the average rate of change to a graph and the instantaneous rate of change to a graph. And also, the purpose of this video is that you understand how the average rate of change becomes the instantaneous rate of change as 2 points come together. So imagine that I was calculating the average rate of change over this interval from 0.5 to, looks like about 1.7. Now, that calculation is what we've looked at before. That's just the average rate of change. And essentially, it's a slope calculation. It's S of B minus S of A divided by the change in the x-coordinate, B minus A. Now, that calculation, as you can see that it's not really terribly accurate because that calculation will be the slope of this line. But the slope of this line is positive. But if we wanted to know what's going on here at point B, well, this positive slope is not going to reflect what's going on at B because the function is clearly starting to decrease there. It's becoming negative. So we would have to move point A closer to point B. And as we did that, the difference from A to B on the x-axis becomes 0. And our average rate of change becomes the instantaneous rate of change, or the instantaneous velocity. You see, here we take the limit as h goes to 0. And instead of S of B, we call it S of A plus h, where h is representing a really small change in the x-coordinate. So S of A plus h minus S of A divided by A plus h minus A. Now you'll recognize that that's just the slope formula, but here the difference h between the 2 points is going to 0. And if we simplify the denominator, you get what is commonly recognized as the instantaneous rate of change, as the limit as h goes to 0 of S of A plus h minus S of A all over h. Because you can see these 2 points, if we move A right on top of B, now the slope of this line does in fact appear to be the same as the slope of the curve. If we were to zoom in, and we'll try this on your calculators in class, this software doesn't lend itself very well to that. If we were to zoom in, you'd see that the tangent line and the curve become indistinguishable. And that is what average velocity is. It's the slope of this secant line. So when we had two different points, that's the average rate of change. And as we took the limit, as the difference between them becomes 0, the average rate of change becomes the instantaneous rate of change, and we have the slope of a tangent line as opposed to a secant line. Okay, Ramblers, make sure that's clear, and thanks for watching. All right, suppose that I wanted to calculate the instantaneous velocity for a particle whose position is given by s of t equals t squared. And I'm looking to do that at time t equals 3. Well, there would be two ways to do it. The first would be to make a table. I could simply perform the calculation 3 plus h squared minus 9 over h, using values just to the left of 3. So I would be 1/10 to the left, or at 2.9, or 1/100th to the left, or 2.99, or even 1,000th at 2.999. And I could calculate the slopes from those 2 points to the point, or I could say from that point to the point 3. Then I could also start on the other side. I could be a whole tenth away from 3 on the right side at 3.1, or 100th away from 3 at 3.01, or finally 1,000th away from 3 on the right side, or 3.001. And when I did that, I would get slopes of 6.1, then 6.01, and 6.001. Clearly, as I come from the left side, I'm coming towards 6, and as I come from the right side, I'm coming towards 6. So I would be comfortable surmising that the average, or the instantaneous velocity, would be approaching 6. Now, that's one way of doing it, and despite the fact that our intervals were getting smaller and smaller and smaller, it would still only be an estimate of the instantaneous velocity. Though it's really small, it's still an average velocity. Now, if we wanted to actually calculate the instantaneous velocity, the only other way would be to use the limit and some algebra. So that calculation would look like this. So when we try to perform substitution on that by plugging 0 in, you're going to see that we get 3 plus 0 squared, which is 9, minus 9 over 0, which 0 over 0 means do something. So we have to apply some algebra. And if we expand 3 plus h squared, we get this. 9 plus 6h plus h squared minus that original 9 all over h, which simplifies to 6h plus h squared over h. Now, I can then cancel the h. And so I'm left with the limit as h approaches 0 of 6 plus h. Now, when I plug in, I just get 6, which is the same answer I got from when I made the table. So I'm pretty comfortable that the instantaneous velocity at t equals 3 is 6. But nevertheless, you could see that only the second way actually incorporated the limit. The first way was just a really, really small interval, but still the average velocity. All right, Ramblers, thanks for watching. I hope that helped.